Alright guys, so welcome back. So we got 10.2 here. We're going to talk about the applications of parametric functions, at least one particular application. We're going to talk about the idea of projectile motion. And this is where it's often used because, again, parametric can talk about what's happening horizontally and vertically with respect to time with talk about the path of this particular projectile. Now, if it's launched at a 90-degree angle, this is totally different then it's just pretty much a pure vertical motion from there. And obviously, we're also assuming certain things like drag, air resistance, and friction, other things going on have no role to play. So this is your perfect scenario in a vacuum, all that kind of stuff that obviously doesn't exist in the real world, but exists mathematically. So horizontal equations you're going to work with is x equals v0 cosine theta t. That v0 or v naught is your initial velocity, and theta is the launch angle you're going to be referring to. The vertical is negative 1/2 gt squared plus v naught sine theta t plus h0. So g is your acceleration due to gravity. You have two different modes. Either you are in the standard English standard form, it's in feet per second squared. And then if you are in metric, then it's meters per second squared. And then the h0 is the initial height, so your starting point. So if we're launching from ground, we're at 0. If we're launching from a certain height, then whatever that height is, that's what we're dealing with. So G, what we're going to work with, G will be 9.8 meters per second squared is what we'll use if we're dealing with metric. And then we're going to use 32.17 feet per second squared if we're in English standard. Those are approximations. So there could be a little bit more accurate values there, and then depending upon your class, sometimes you might just approximate G as 10 instead of 9.8, so it's a nice number, and then 32 as well, so it's a nicer number. But for our purposes, we're using 9.8 and 32.17. So we've got a soccer ball kicked across the field at an angle of 30 degrees, initial speed of 25 meters per second. So because it's meters per second, our G is going to be 9.8 meters per second squared. So part A wants to write a set of parametric equations for the motion of the ball. So your horizontal motion is, again, v0, the initial velocity, which is 25. That's what this represents. And there's our theta. So this would be 25 cosine of 30 degrees t. And, well, if it's a nice unit circle angle, like 30 degrees, 45, 60, and so on, then we can rewrite that. Cosine of 30 is root 3 over 2. So this would be x is 25 root 3 all over 2 t for my horizontal motion. My vertical motion is negative 1/2 times 9.8 t squared plus 25 sine of 30 t. And then my initial height is 0 because it's launching from the ground. We're kicking a soccer ball. Typically, it's on the ground. We're assuming you're not kicking in midair or anything like that. We're on the ground. So the negative 1/2 of 9.8 is going to give us a negative 4.9 t squared. You're always going to get a negative 4.9 when you do the negative 1/2 of 9.8, so you can kind of just skip right to there. And again, sine of 30 is a half, so we can write this as 25 over 2 t. Now, in both those cases, if you want to write it as 12.5 rather than 25 over 2, that's perfectly fine. But those are our equations for part A. Now, B, C, D, and E, we're using this information and a graph to figure out what's going on here. So for part B, how long was the ball in the air? You're looking for when does the Y value hit 0. So we're going to set our negative 4.9 t squared plus 25 over 2t equal to 0 and solve. Now, in this particular case, we can factor and solve it because they both have a t in common. But if there was an initial height, we probably would not be able to factor this thing. So for each of these questions, what you're going to do is you're going to graph the y equation. And the y equation is going to give you answers for B, D, and E. The answer you get from B is going to use for answer of choice C. So when you graph this thing, you're going to see some sort of parabola. So your graph is going to be kind of looking like this shape right here. Now, where that parabola goes, it's going to entirely depend on the information in this particular question. So you might have to adjust your window based on the initial speed, the initial height, the launch angle, all that kind of stuff. For my window for this thing, I have my x's go from 0 to 10. So my x min and then x max. For my y's, I have it going from 0 to 20. So my y min is 0, and my y max is 20. So that kind of gives me my window there where, so instead of seeing the full parabola like this, we're only caring about the first quadrant. Generally, you only care about the first quadrants. Mathematically, in terms of the real world, quadrants 2, 3, and 4 are not realistic. Quadrants 2 and 3 imply time is negative, which can't have. Quadrant 4 implies the y is negative, which in case the ball is burrowing through the ground, which, okay, might theoretically happen given enough speed and the ball being big enough and dense enough, but not really realistic in a soccer ball case. So we only care about the first quadrants. You'll find that where it's crossing right here, that value of t you'll get right there. That's the answer for part B. So that's what we're looking for. So you do your zero calculation on your graph. You'll find that value when we round to the thousandths place is going to be 3.061 seconds. And then we fill that answer into the x equation to say how far the ball traveled in the air. I want to know what is the horizontal distance. So our x value would be that 25 root 3 over 2 times that t value 3.061. Which when we work out that mathematically, we get 1.531. Oops, wrong thing, sorry. We get 66.273 meters. I was looking at the answer for part D. Sorry about that. So again, where it crossed the x-axis, technically the t-axis, but on your calculator will be crossing the x-axis. That's the answer for part B. You take that answer around to the thousandths place, plug it into the x equation for part C. And now when it's talking about the maximum height, that's going to be the vertex points, where the x corner of the vertex is the answer to part D, the y corner of the vertex is part E. So when you look at do your vertex calculations, you do your maximum. And again, refer to my video page on using the calculator for finding max and min, as well as the intercepts, if you're not quite sure on how that works. You'll find that the maximum point, that location there, time-wise, that's the 1.531 seconds that I said earlier. And the location of that, the y value, is part E. That's going to be 11.48 meters. Now, since you do have a quadratic, you also could calculate t by hand without the use of looking at the graph, because that's your negative b over 2a calculation. So negative b, so it'd be a negative 12.5 over 2 times negative 4.9. That will give you the 1.531 if you do that full calculation there. And then plugging that into the negative 4.9 t squared plus 25 over 2t equation gives you the 11.48. But you're generally going to use the calculator for all that. All right, so that's our scenario given a nice launch angle and no initial height. So obviously what would change here if I had an initial height, I would just have a number adding on with the y equation, which will make into some adjustments for where everything goes. And if the launch angle is not nice, then instead of knowing what cosine of 30 is and sine of 30 is, I would leave it in its trig form there. I would make sure my calculator mode was in degrees so I can properly see it, and I calculate my answer from that. And that's what we're going to look at here. So a cannonball is fired across a flat field at an angle of 56 degrees, initial speed of 42 feet per second, initial height of 8 feet. So we're going to use g is 32.17 feet per second squared for our g value. So theta is the 56 degrees, not a nice angle. My initial speed is the 42, and my initial height is the 8. So when we take a look at our equations here, the horizontal equation, x is your v0, so 42, cosine of theta, 56 degrees, t, and we're going to leave it exactly like that, so we have an exact value to work with. Our y equation is our negative 1/2 times g, which this time it's 32.17 because we're in feet per second squared, t squared, and then plus our initial velocity, the 42, sine of our angle, which is the 56, t, plus our initial height of the 8. The only thing we really can do with that is take negative 1/2 of 32.17, which would be negative 16.085. And because of the extra decimal right there, it's why a lot of times, depending upon the class, you might just simply think of g as 32. So the negative 1/2 of 32 is negative 16 rather than having these extra decimals. But what our textbook is using, what the different worksheets we're doing for homework is going to use 632.17. So I want you consistent with that. Now, when it comes to the graph of this thing, again, we're only looking at the first quadrant. We're again creating this parabola right here. Remember, this part down here is the answer for part B, and the vertex point is the answer for part D and E. We're taking B and plugging in to get C. Now, my window for x's, my graph, I'm doing 0 to 5 for the x's here. And then for my y window, I'm going to go from 0 to 40. Trial and error really to figure out which ones you want there. Start at 0 to 10 for them both and kind of adjust it based on that. You see it kind of going in pretty quick, then maybe you don't need to go all the way 0 to 10 for the x's. You see it cut off, so you don't really see the peak and everything. You need to expand out the y's. Just kind of adjust from there. So part B, when we find its intersect point, so using the calculator there, we're going to get our t value to be 2.374 seconds, which we then plug into our x equation, so 42 cosine of the 56 times that 2.374, that's going to give us 55.756 feet. Part D, the maximum point, either by doing negative b over 2a, so by doing negative 42 sine of 56 divided by 2 times the negative 16.85, or using the calculator, where's the max location. Either way, you're going to get 1.082 seconds. And then our y value, either taking that to plug into the y equation or, again, looking at the maximum location, which is the y coordinate of the max there, you're going to get 26.844 feet. So again, with the windows, I adjusted 0 to 5 and 0 to 40. As long as you can see everything, you could have done different windows. So like 0 to 30 would have been fine for the y's. The max is 26, so anything a little bit above 26 is perfectly fine. The x's only go as far right as 2.374. It's when it hit the x-axis, so you could do it like 0 to 4 and be perfectly fine. It's whatever you need to see best. And if you have small initial speed, you're going to need to have small windows. No initial height, stuff like that's going to totally adjust how it looks. All right, so that's how we're using our parametric equations with projectile motion. And that's really the extent of what we're doing with our parametrics. So next up, we're going to get into some of the polar functions. We'll get into the idea of plotting them to be able to get into graphing. That's really the next two topics, 10.3 and 10.4. So I'll see you guys next time for those.